Yeah, so good evening, everyone. So first of all, I want to thank Sunny for hosting this meetup and giving me this opportunity to present the project where me and my team are currently working on, which is called SpaceCraft. So we're actually building a real-time collaborative REPL, and we don't know what that means. That's okay, I'll go into detail. So what is SpaceCraft? It is an open source collaborative REPL. REPL is a Read-Eval-Print-Loop, which is a program where you can enter code into a console and then it will return you the evaluation result. An example would be IRB or Node.js interactive REPL console, and for Python has that too. So what we're building here is we want to build an in-browser real-time collaborative REPL such that no setup is required. So this is to encourage developers to come together and pair program, and also maybe interviewers and candidates can have a really quick interview session without having to install the runtime necessary. We support Ruby, JavaScript, or Python as of now. We plan to support more languages in the future. And we built this with Node.js, WebSockets, and secure using Docker. So currently there are a few existing solutions in this space. And I'll go through each one of them and tell you why they are not ideal. So first of all, we have REPL.it. REPL.it basically is an IDE, which is a development environment for people to execute code, run multiple files and all that. However, they don't have collaboration feature, which makes pair programming impossible. While they are full development environment, we're not focusing on that. We're building a single page, single session REPL and collaborative environment. So REPL.it has all these problems that we're trying to solve. CoderPad, however, provides an in-browser REPL and it's also collaborative. However, in order to use CoderPad, you either have to only use a 30-minute free demo, or if you sign up for it, it only allows you to have restricted access. That means limited paths you can create, which is what we're trying to do here. We're trying to create an open source alternative so that users don't need to sign up. Now, high-level goals is we want to enable a terminal-like interface for code evaluation. And I'm going to detail on how we build that in just a minute. Secondly, we want to enable multiple users to come together and collaborate in real time. And third of all, we want to synchronize displays across different users. There are a few challenges associated with building such a project. First of all, we want to isolate individual users' sessions from one another. Basically, we don't want user A to go into user B session if they're both in different sessions. Secondly, we want to prevent malicious code from affecting our host system. Since we allow users to enter code into our system, we want to kind of isolate that from our host system. Lastly, we want to achieve real-time code execution of a latency goal of 150 milliseconds or less. Now, before going to how we build a REPL, I'll just quickly touch upon network architecture that we choose and why. So we chose to go the client-server architecture. It makes more sense for our use case. And there's this consideration between HTTP or WebSockets as a network protocol. In fact, we built a prototype with HTTP, and we have one WebSockets as well. We found that WebSockets fit our needs better because of the few reasons which I'll explain in the next slide. So as you can see, the HTTP, every time the client expects a response, the client has to send a request. Each payload is around 200 bytes. That's a lot. With WebSockets, however, only initial HTTP handshake is required, and after that, either the client or the server can initiate the sending of data. The payload that's sent with the data is only about 2 to 10 bytes. So this leads us to the advantage of using WebSockets, right? So why WebSockets? As I mentioned earlier, it's low additional payload of 2 to 10 bytes per request. And since we are sending data frequently between the client and server, we'll take advantage of that. Real-time communication is very important. Secondly, it supports bi-directional communication. That means we can stream data from the server to the client directly without having the client to necessarily make a request. Lastly, which is the most important point, is that we can very easily detect a client disconnection. And when that happens, we want to initiate teardown and shut off our application so that we can free up resources. With HTTP, however, although it's possible, it's more difficult to do so, as we have to have the client continuously ping our server, which may cost a lot of bandwidth. So with that getting out of the way, now we need to ask this question. We have the client and the server. Where should we execute the code in? Remember back to my point where when we want to build an in-browser REPL, we have the choice of running the REPL all within the browser, or we can run the code in the server. Now, if we exploit with executing code in the browser, but we found that it's not feasible because when we run an in-browser compiler, it's going to increase a lot of burden on the browser. What this means is that when you execute computation-heavy code, such as infinite loop or some sort, it could slow down potentially and enhance the browser. Secondly, it's not very scalable. For each language added, it's around 15 megabytes for each runtime. So browsers download all of them. And also, not all languages come with in-browser compiler. What this means is that what if I want to add Go or Crystal or Haskell? If they don't have an open source alternative to an in-browser compiler, then too bad, you can't do that. In fact, Vincent Wu, which is the founder of CoderPad, says in one of his interviews, he says, what are you going to do? You're going to compile your programming language into JavaScript? Well, good luck with that. And therefore, leads us to a decision of executing this code on the server side. And the reason for this is so that it's easier to manage multiple runtimes. We can very easily add more languages as we need. And it's also very scalable. We have more server resources, more available than just running everything in the browser or in the client side. The client doesn't need to download anything. However, that's a slight trade-off, which is you increase our server overhead. But for our use case, it's manageable. Now, here comes the interesting part, which is how we actually build a REPL. So for front end, we have two sections. On the left-hand side, we have terminal display. We're going to leverage xterm.js, which is a framework for basically converting text and CSK codes into something like a terminal. On the right-hand side, we have a text editor, which we use code mirror because it supports syntax highlighting and some line numbers and all that very nice features. Now, as you notice, we don't have any code evaluation logic on the front end. It's just pure UI. Now, next question is how are we going to evaluate code if we don't have any logic in the front end that is code? This is an important point because from a regular interaction perspective, like user, for example, you would enter, you would spin up IRB in the console, and then you would input directly into the console. The console outputs the evaluation result. This is very different from what we're building here because since we're allowing a remote service, we have to basically do all of that manually through our application code. And the flow, basically the flow input output looks something like this. We have the client, and the client say, hey, I want to know what's the result of 123.map, and then I pass in the string function. And our application will say, well, we'll ask the REPL program and say, hey, what's the return value of this line of code? And the REPL program will say it's this value. And our application takes that and then returns to the client. So this way we can ensure consistent output, right? But there's more challenges to this, which I'm going to more into detail into why. So the question comes, how does the app actually communicate with the REPL program? Now, there are three approaches which we discovered. The first one is pretty obvious. It's just using languages built in REPL API. For example, Node.js provides a REPL module where we can include application code, and we can call methods and pass in the code, and then we can call some other methods, which then will return the evaluation result. Problem with this is that the application has to be written in that language. If you were to run Python, however, you'd have to use the Python REPL module. If you were to run Ruby, we have to write all of that in Ruby. So it's not scalable because every time we add a new language, we have to rewrite the entire application with that language or leverage external libraries, which sometimes may not be available. This leads us to that approach number two, which is what we basically do is we spin up a REPL process on the backend, and we can basically write to its standard in and read from its standard out. So REPL programs are like processes, right? When you spin up IRB in the terminal, for example, it's actually spinning up another process. It's called IRB, and the process has a standard input and standard output. Standard input is basically allows you to write code into it, and the standard output allows you to read the evaluation result from it. Now, while this sometimes works, there are a few problems with this. The first problem is that the streams may be blocked, which lead to hanging outputs, which I'll show you in a little bit how this happens. Now, there's a few reasons why this may happen. I won't go into too much detail on that, but it's potentially caused by probably a lower level compiling language that is such as C. So for example, Python is written in C, and then the C implementation says block the outputs until new outputs is coming in. Therefore, it's not scalable because if we are hanging outputs, we have to use different techniques to unblock those streams, which and those techniques differ from language to language. So for example, from Node.js, we would pass in interactive flag when we spawn the application. For Python, we do some other tricks to it. Therefore, the complexity increases for each additional supported language. Now I'm going to show you a demo on how this happens, right? So we're going to spawn the child process when spawn node. We're going to write the console log 2 times 3 into the standard input. Now when I run it, you see that it hangs the output. But when I unblock, when I close the input by calling and when I run it again, you can see the output comes out. Isn't that weird? And now let me show you what if I spawn IRB. Now I'm going to write a Ruby, some Ruby expression, which is P2 times 3. Now as you can see, the full output is shown in our terminal, right? And there's no difference even if I close the input, as you can see right here. Now what about Python, right? Maybe wondering. So now I'm going to spawn a Python REPL, and I'm going to write 2 times 3, print 2 times 3, and those keep the input stream open. You can see the output is hanging right now. Right, it's hanging, it's no output. But when I close it, you can see the output is displayed. So So this problem is this, because if we close the input stream and have the output, then we can't write any more code into our program. But if you leave it open, then we have to figure out how we can unblock that. So this leads us to our final approach, which is we're going to interact with the pseudo-terminal. Now, what is a pseudo-terminal? A pseudo-terminal is basically a program that acts like a communication channel between our application code and the REPL process. So our REPL program, they want to be persuaded that the input is in fact coming from a terminal. So with the pseudo-terminal, we can do that. So we're going to have our application write and read from a pseudo-terminal instead. Now, there are a few advantages with this. First of all, we're going to eliminate all the handling of the certain input and output streams. All that mess can go away. And we're also able to send control sequences such as control C from our application to the REPL program. And it will work as if a user is typing control C on a terminal. We can also capture all the outputs from the REPL program, includes colors as well. The trade-off is that there's slightly increased overhead because you're putting additional layers of processing between the application code and the REPL program. But that's okay because with all these advantages, we feel like it suits our use case. Since we are supporting multiple languages, we want to make sure that the output is consistent. To just recap what I just said, we can expect a regular user interaction with REPL to look something like this. A user, so let's say you're splitting out IRB, you will enter some command into terminal, and the REPL program is an IRB, which then will be, so the terminal will send the input to the REPL program, and the REPL program will communicate with the terminal, which then will be displayed to the user. So in order to simulate this, we use a pseudo-terminal in place of a terminal. That way our application can send code to our pseudo-terminal, and the interaction with the pseudo-terminal and REPL program will be the same. And so we can expect the same outputs to be returned to our application. To give you a demo, I'm spinning up a new a pseudo-terminal with node spawn and connected to a pseudo-terminal. I'm going to write 2 times 3 with a new line character to it. As you can see, we receive the full output without having to do any more tricks to it. Like a small IRB, we can expect the same, right? Full outputs. And if we do it with Python, we can expect Python to work as usual too. So with the pseudo-terminal, it solves basically a lot of our issues here. It produces full outputs regardless of chosen language, which is ideal for our use case here. With that getting out of the way, we can now think about synchronization and collaboration. So we're going to go through quickly on how output is synchronized among clients. So, so as usual, we have the client request a line of code to be evaluated, right? So the line of code goes to a pseudo-terminal, and this is just little snippets of code which we in our project, and then our application receives the evaluation output from the pseudo-terminal, right? And then from there, our application can say, I'm going to broadcast this result to all connected clients. So application outputs, broadcast outputs all connected clients through WebSockets. And then finally, we can display the output on the UI. Now, while output synchronization seems pretty straightforward, input synchronization is a little bit tricky. So I'll give you an example here. For example, a user presses the key, open square brackets, right? So in the client's terminal, we'll do something like this. What we're going to do is we're going to update the state of within the client, and then we're going to write it in the client's terminal. So with that, the client will also send an event indicating that the line has been changed. with the current line. Our app server will receive that line, and then our app server will also compute the prompt from the previously cached output. Now, why is this important? This is important so that we can rewrite the entire line by rewriting the prompt first and then the line. So, although there are other ways to do that, we feel that this is the cleanest way because we're resetting the entire line every time the client presses a key. With that, we can broadcast the current prompt line to other clients. And when other clients receive the line of the prompt, we write that. We update the state of the other clients to include that new line. And we basically want to say, clear your current terminal line, and then set the terminal prompt with the current prompt before writing the line. This way it provides a very clean update. So although we thought about, we could maybe you could write the number of backspaces equals to the length of the line. That could potentially work, but what if two clients type at the same time? Then if two clients type at the same time, we need to decide whether or not to write 2 backspaces or 1 backspace. Now, we don't want to deal with that, so we just rewrite the entire line. Now, with synchronization is successful, we want to look at the container architecture. Now, for those of you who are not familiar with containers, that's fine. I'll explain what it does, why it's important in our project. So why we choose to go to a container-based architecture? First of all, there's a few problems with running the app in the host environment. So if we just run our app regularly in our host system, if let's say we have a user that enters some malicious code, for example, to remove the entire root directory and file system, that could be very dangerous. And even if we're not giving the user root access, let's say an attacker performs dirty code exploitation and gains root access from that, the attacker can compromise our host system. It's also hard to limit resources for each individual user session when running the app in the host environment. And also, this is the very last point, which is very important, which is if we have a single user session that takes up all of the CPU or the memory, that will potentially compromise our server and all of the other sessions. That's why we chose Docker. So chose Docker because it's the most it's well established, good documentation. Comes with a lot of good advantages. And now comes to questions of why containers, which just goes back to the same point. Containers provide isolation between our application instances. What this means is that when you want to spin up multiple rooms so that multiple users can collaborate on different rooms, we need a single room to have all the runtimes and dependencies associated with it. So, for example, we need a Linux OS, we need Ruby, JavaScript, Python runtimes, we need our application. We can very easily bundle that with Docker. File system also contains, so when running our application, users will not have access to the root, to the host file system by default. Containers have significantly lower footprint than a virtual machine. So you might think that one of these virtual machines, right, it provides similar isolation. But the problem with virtual machines, we're talking about gigabytes here versus megabytes for containers of storage space. We can also add security measures to strengthen our isolation. And we can very easily limit memory and CPU usage for each applications with the Docker CPUs. This is important because if we lower the limit, we can have more reserved resources. We're able to run more application instances. And if, let's say, a single user session spikes in terms of memory or CPU usage, it will affect the single container that has the application, and it won't compromise other rooms. So this is a simple diagram which should demonstrate what I just talked about earlier. So let's say a malicious attacker gains access to one of our containers, right? So when the attacker compromises that container, only users that's connected to that container will be affected, while users in the other rooms will not be affected. Also, a resource spike in a single room will not affect other rooms as well. So users in other rooms will kept safe. Now, containers are not a magical pill. Of course, there's security risk with containers. Containers are not a sandbox. And why is it so? It's because applications that run inside a container, they access the system resource the same way that a non-containerized application do. And this is achieved by the application making system calls directly to the host kernel in a privileged mode. This is potentially dangerous if, let's say, an attacker gains root access within a container. The attacker may have the opportunity to access our whole system. So a container escape is possible with a single vulnerability. So currently our app looks like this. We have our application containerized with Docker, and then our application is going to make system calls to a host kernel. And this is going to have some isolation, but it's going to be weak. So what we're going to do is, first of all, we're going to lock down our containers by providing users with non-root access. We're going to use namespaces to run as a non-root user so that we can reduce the attack surface. This is an example Docker file that allows the container to be run as a non-root user. But of course, we want to further lock down our container and increase the isolation by using container runtime sandbox. So basically what it does, container runtime sandbox, what it does is that it basically intercepts all application system calls and employs rule-based execution. What this means is that if an attacker has an opportunity to make privileged system calls, on the container runtime sandbox will see that immediately and intercept and block it. With this, you can access guest kernel, provide unprivileged access, slightly increase overhead. And again, despite our use case, we're not doing any heavyweight usage. So, so just briefly illustrate what I was talking about. We have our containerized application, and we're gonna put a container runtime sandbox runtime in the middle. gvisor is an open source container sandbox runtime that's developed by Google, and it acts as independent guest kernel, which enforces unprivileged access. That way, the system calls when it goes to the host kernel, we can make sure that it's all unprivileged, and minimize the attack surface even further. Now, with all that said, we want to figure out a way to connect the users to our containers. Now, there are a few ways we can do that. The most straightforward way is to use port forwarding. Basically, we open up a port in our host system, and then redirect that port to the port that's associated with the container. Now, the problem with this is that it's not a good design because the ports are predetermined. That means anyone could just do a full port scan of our on the server, and then find out which ports are open, and then be able to access other rooms. This leaves us with little to no privacy, and therefore we switch to another approach, which is using reverse proxy. So what we're going to do is going to build a web server that sits in between the user and our application. So the web server acts as a reverse proxy, and basically, when the user requests makes a URL request, it goes through our reverse proxy, and that reverse proxy will determine which container that that we send the request to. A reverse proxy can also act as a load balancer as well, and also cache some important content. This way we can abstract away the URLs and all that to ensure privacy of the groups. This is a simple diagram to illustrate how this all works. First of all, the client is going to send HTTP request to a proxy, and the US proxy will receive the request and then reads that URL and say, okay, we'll forward you to this server, to this particular container. Once that's done, the server is going to send a response back to the US proxy, and then the proxy guards the response with pattern. Excuse me. So, so when the client requests URL, the reverse proxy will take the request and reach the server on the client's behalf. It regulates client's traffic and routes HTTP sessions to the container, and then we can connect users to a containerized application through WebSockets for further communication. So once a client knows, once a reverse proxy knows which container that it wants to forward the URL to, the client will establish a WebSocket connection with the container, and we can now the reverse proxy is no longer needed. So this project is still under development. We're still iterating through our project. So future work includes we want to add remote cursor for user identification while typing. We also want to enable the user to download or upload code from a file, and also support more languages such as Go, Crystal, Rust. And for compiling languages, we like to figure out the process of how to handle that. With all that said, let me just spin up a demo so that you guys can see our current prototype. So just refresh this page. So on default, it's been some IRB. So if I type something in, here, right? If I just do like a Ruby evaluation, you can expect the output to be returned immediately. Now all of this is running remote server, by the way. And now I'm going to spin up a second client. I'm going to show you the side-by-side comparison. So now we have two clients running at the same time. What if I type something in the other client? You can see that inputs are synced across in real time. And then when I do when I evaluate, both clients will receive the same outputs. Now for the text editor, I can also write code into it. I can write a method. So let's just call this method hello, and then it's going to just print the string plus hello. Now we run this. All the code that's in here goes into the REPL, and then it's run. So now I reference hello and call it. You can see that, in fact, it calls the method that we defined earlier. Last of all, I'm going to show you the shell, which is experimental feature. It's just for testing purposes. Now we're in root in our app directory, right? The user still has read access, but if the user tries to create a folder, you can see the permission is denied because the user is non-root, right? We can also do create a file, permission denied. What if we try to remove the root directory of the system? Well, use no preserve root. Okay, sounds good to me. I'm just gonna do that. And you can see that everything is, all of the calls are denied, basically. So our security measures are working. And yeah, so that's our demo. So I lost that. right here. So thank you all for attending this TED Talk. Feel free to contact me if you have any further questions. And this is our GitHub page. Our website is still currently under development. You can expect to check back in a couple of weeks. And now I'm open for Q&A.
So you mentioned before you're going to get a pseudo-terminal. What does that mean exactly?
What is a pseudo-terminal?
Yeah.
So a pseudo-terminal is it's basically like a device, right? Right now it's a program because it's running as a program that acts as a communication channel between our application code and the REPL program. So without a pseudo-terminal, the application code has to manually handle the standard input and output streams of the REPL program. But with a pseudo-terminal, we offload that so that the pseudo-terminal handles all of that for us. What we need to do is we basically write code into the pseudo-terminal, and then the pseudo-terminal will handle that for us, and then whatever that's evaluated from the REPL program will come to our pseudo-terminal, and our application code can read directly from pseudo-terminal.
Are you using a library for this?
Yeah, we use a Node PTY, which is library to instantiate pseudo-terminals. Any other questions?
So what if I don't really know how this will work, but with conflict resolution,
right?
I didn't quite follow how you were managing that.
Oh, that's a good question. So so back to probably show you a slide to better explain it. So we have two parts of our application here, right? The left-hand side is the terminal, and the right-hand side is the text editor. Now we're asking about conflict resolution on the terminal or the text editor, or both.
Yeah, well, because they see everything.
Yeah,
everything.
So for the terminal, we don't do conflict resolution. The simple reason being is that for our use case, we don't expect two users to type at the same time. It will be chaotic, in fact, for both users. Imagine like having you and me typing at the same time into the console. There will be chaos. Right. So in a normal use case, you don't expect that to happen. Even if that happens, a client can see immediately that his input is being override, so he knows that someone else is typing. Now, for the text editor, however, we need conflict resolution. In fact, we utilize YJS, which is a shared anything collaborative framework that uses CRDT. They use something that's called like a Read-Eval-Print-Loop. And we use it because it integrates nicely with WebSockets and also pretty performance. So with that, even if two users were to type at the same time in the text editor, the conflict would be resolved by that framework. Any other questions?
Yeah, so can two people essentially on both consoles be typing in the text editor on different lines at the same time in this current implementation?
Yeah, exactly. So if one person types something and then another person types the same position, those conflicts will be resolved, and then both clients will see that both their inputs will be shown.
In your shell terminal, can the user do anything with the shell? Or because of all the examples you showed, the permissions are not, but was it just for testing purposes, or can the user say can they do an echo command, or is everything blocked for the shell?
For now, the user can still execute something in echo, definitely, and all that. While we're still thinking about ways to try to lock execution as well and all that. But for our use case, it's pretty good to give the users root access. So even if the user have they execute malicious code within our terminal, since it's run in gvisor, it basically intercepts everything that's potentially malicious, so that it doesn't come to our host system. So they could compromise the container however they want, but it's a lot harder to to hack into our host system. Did that answer your question?
Yeah. And with gvisor, does it come with like, do you configure what you will allow the user to do calls, or does it come with like kind of blank slate, like the user can't read any of this stuff?
Yeah, it comes to a blank state where a user can do anything, and then there are definitely more configurations that we can limit, like specific system calls and all that. But for our use case, we're not dealing with sensitive user info and all that, so we just let gvisor handle that for us. Okay.
This is really impressive.
Yeah.
Thank you. It's cool. So if there's no further questions, wrap this up, and I hope you guys enjoy.
Thanks.
Cool, thanks.
So yeah, that was it. Like with this talk, I mean, we don't have anything more planned for the meetup, so if you could just feel free to hang out a little bit. I'll probably